right? So basically we can think of, right, each column of these matrices as a vectors, right? Like 1 5 2 is one vector, and 2 6 4 is another vector, and then 3 7 2, and then 4 8 3. They are all the vectors what we consider from the matrix. They are all the column vectors. We can think of the space spanned by these vectors, right? Means the linear combinations of these vectors, right? Alpha 1 times this plus alpha 2 times this plus alpha 3 times this vector. Let us consider this is a vector v1, v2, v3 and then v4. What I am telling here is the scalar combinations, scalar, right, linear combinations, alpha 1, alpha 2, alpha 3, alpha 4, right? For these are real numbers what we are considering. We are only the real numbers in this case, right? The numbers are real numbers and the scalar values are also real, right? Alpha 1, alpha 2, they are real numbers, right? So the linear combinations of these vectors forms the space for, right, for all values of, right, alpha 1, alpha 2, alpha 3, alpha 4 belongs to what? Some real number, or, right? So you get a space. This space, vector space, what we are considering here now is what we call as column space of the matrix A, right? So this is what I am writing here, column space of this matrix A, right? So each vector now in this case particularly, so more general it is m cross n, right? This is a typical example for m equal to 3 and n equal to 4, right? So each vector size, having 3 elements in this case, in more general it is going to be what? M elements, right? Depends upon the number of row. Each vector is going to be like that. So this is of, Rm is a complete space. Rm is a vector space is of what? The complete space with the vector with what? M elements, whatever the vector you consider, right? That forms that complete space Rm, right? That has 0, right? Everything. The restriction is what? I mean, the condition is you must have m elements in that vector. That is going to be your Rm. And this column space of A is going to be the subspace of this Rm. It may not be the complete space, right? So I am doing linear combination of these 4 vectors, but need not end up with what? The complete Rm. So it is going to be what? The subspace. That's what I have written here is the subspace. Column space of A is going to be the subspace of Rm. This is that Rm space, right? And your column space of A is going to be the subspace of Rm, right? And now we can think of again Ax equal to 0. This is of size m cross n in this, and this is n cross n, right? The set of all vectors, right? The set of all vectors x such that Ax equal to 0, right? Satisfying this condition, and this forms a space. This forms this vector space, right? Set of all values of x satisfying this Ax equal to 0. 0 is a vector here, right? This is m cross n, this is n cross 1, this is going to be m cross 1. So set of all values of Ex satisfying Ax equal to 0 is what we call it as null space of the matrix A, right? We discussed about this column space of A, and this is what we call it as null space of A. And the number of elements in this space is going to be what? N cross 1, right? So I am looking for, right, Rn is a complete space with vector filled up with what? N elements. And this null space of A is going to be the subspace of what? Rn, right? You got it? Right? So n elements in a vector in this case, right? You see that's x and you have n elements, n cross 1, isn't it? So set of all vectors x satisfying Ax equal to 0, right, that forms a space, linear combinations of, right, the vectors satisfying this condition that forms the complete space, and that is going to be the subspace of Rn. We have another two space. In this case, what we are going to do is we are going to collect the vectors what? Row wise, like this. So in this case 1, 2, 3, 4 is a vector, 5, 6, 7, 8 is another vector, 2, 4, 2, 3 is another vector. So you are actually collecting the vectors row wise, right? If you think that, if you take the transpose of this matrix A, in that case these vectors are actually becoming what? The column. The row space of this matrix A is same as that of what? Column space of A transpose. So I can think of another two subspace, which is column space of A transpose and what? Null space of A transpose. Another two subspace we can consider, right? So that's what I have written here, null space of A transpose here. This is already I told null space of A, and this is going to be your column space of A transpose. Because, so what about that elements, number of elements in the vector, right, satisfying what? The condition of this form, right? I am just writing that expression. You can write it as A transpose Y equal to 0, and this is n cross m, and this is going to be what? M cross 1. It means that the null space of the matrix A transpose is going to have the number of elements in the vector is going to be what? M. So it is going to be the subspace of Rn, right? So you have column space of A and null space of A transpose, both are going to be the subspace of Rn, and the column space of A transpose and null space of A, they are going to be the subspace of Rn. So this is the four fundamental subspace of the matrix A, and I have drawn in this form with one point as a common for both the space, and this vector is what we call it as vector 0, right, which is present in column space of A as well as what? The null space of A transpose. And this is what we call the 0 vector here, and this is also the 0 vector. But the difference is there. This 0 vector has m elements. It is a vector with 0, 0, 0 m elements. And this is a 0 vector with n elements, right? So both are different. Okay, but this is the common for column space of A and null space of A transpose, and this is common for column space of A transpose and null space of A. And I have drawn in this form, to indicate that they are orthogonal subspace. They are orthogonal subspace. It means that if I have a vector u in this and if I have a vector v in this, then u transpose v, right? The dot product, if I do, that is going to be end up with what? 0. They are the orthogonal subspace. So see, it is like, for example, you consider column space of A is going to be u here, right? And similarly, any vector you consider in this u and u1, let us say this is u1 v1 here, and this is u2 v2 here, right? So they are again becoming orthogonal. It means what I am trying to say here is u1 transpose v1 is 0 and u2 transpose v2 is 0. That's the meaning of it, right? We can of course cross check that, right? So v2 is in the null space of A, right? So I can write it as what? A v2 is what? 0. This is granted because v2 is in the null space of A. What we need to prove is, we need to prove u2 transpose v2 is going to be what? 0, is it? Right? So if I consider a transpose, v2 transpose A transpose here, right? That is going to be our 0 in this, and v2 transpose, right, A transpose let us say some arbitrary vector x here, that is also going to be your 0 in this. For some arbitrary vector x, I am claiming that A transpose x is going to be what? U2, because U2 is in the column space of what? U2 is in the column space of A transpose. So for some vector Ax, right, I can look for what? A transpose X such that that is equal to what? U2, right? So it is becoming what? V2 transpose U2 is equal to what? 0. In fact, this is what? This is a matrix, but when it comes to this, it's going to be that scalar value, right? So you are choosing in that way. So this is going to be a scalar. So V2 transpose U2 is going to be that 0. I hope this is clear to you. What I am trying to say here is the column space of this matrix A can be represented in another form, just like what? A into X is a vector which is in the column space of A. The matrix A, yeah, here for example, matrix A, if I multiply with this vector X, where it goes? It goes to that column space of A. Are you getting this? A, the matrix A into the vector X, right? That can be represented. What I am trying to say here is, let us take the same example, right? So 152, 264, 372, and then 483. This is multiplied with what? X1, X2, X3, X4. This is the vector X here, right? This I can write it as X1 into 152 plus X2 into 264 plus X3 into 272 plus X4 into 483. It means what? I am doing linear combinations of the column space of this matrix A. You got it? So if I multiply the matrix A with X, A into X, what it really means by that is I am actually mapping to the column space of A. You got it? Both are same. Both are same, right? The way how I write this and this is going to be the same. You can cross check, right? So because you see this row multiplied with this column, right? 1x1, 2x2 plus 3x3 plus 4x4, right? That is there in the first row. And similarly when you get the second row, and if I take that constant outside, x1, x2, x3, x4 outside, you get what? x1 times the first column plus x2 times the second column plus x3 times the third column plus x4 times the fourth column. That step you can write it, right? You just multiply and make sure that they are the same, right? So now I hope you are getting, if I multiply this vector x, right? Got it? If I multiply this vector x with the matrix A into X, that goes to where? The column space of A, right? So this is column space of A here, right? So some arbitrary vector, if I consider X, and if I multiply A into X, that goes directly to this. Ax will be there in this column space of A. That is the meaning of it, right? So that is what I said here. A transpose X, where it goes? It goes to the column space of A transpose, that is here. Here it goes. That vector lies in this space, right? What I am claiming is for some vector X, A transpose X, right? I call it as U2, that lies in where? The column space of A transpose. Or put it the other way around, I have chosen U2 is in the column space of A transpose, right? That's what I have chosen, no? Column space of A transpose. It means that there must be some vector X which I can write it as what? A transpose X equal to U2, right? So in that case, if I write like this, then automatically what is happening? V2 transpose U2 is becoming what? 0. It means that they are the orthogonal space. If I choose one vector from here, one vector from here, if I do this dot product, it will end up with 0. In the same fashion, we can prove it, that I leave to you. If I take one vector from here and one vector from here, if I do this dot product, that is going to be 0. This is the reason why I have drawn in this form, right? So now, how to find out this fundamental subspace? So you have, say, matrix. I will consider this matrix here, right? What I do now is I multiply here the identity matrix, right? So this is 3 cross 3 and that is going to be 3 cross 4, right? So now what I do is I apply the row reduced echelon form on both sides, right? Such that, so what I want to do is I want to make this to be 0 here. So I multiply, right? It is like this. R2 is R2 minus 5 times R1. This operation I wanted to do, right? So this matrix will do it. So if I apply this one to this matrix, you get here as 1, 2, 3, 4, but this one is 0, and here 6 minus 5 times 2 is 10 minus 4. Correct me if I am doing some mistake. 7 minus 5 times 3, 7 minus 15, it is minus 8, and then 8 minus 5 times 4, right? 20, it is minus 12, right? So this is row reduced echelon form. That is what I am doing. And similarly, what I want to make it is this one is 0 here, right? So what I do is I apply this R3 is becoming R3 minus 2 times R1 here, 2 minus 2 times the first row, that is becoming 0 here, and 4 minus 2 times the first row, that is also becoming 0. And then here 2 minus 6, right? It is minus 4, right? And then 3 minus 8, right? It is minus 5, right? I am trying to represent that final matrix in the form of what? The row reduced echelon form. Right. Here the same operation I wanted to do here. This is 1 0 0. So what I did was R2 minus 5 times R1, right? So this is minus 5. This is right, R2 minus 5 times this. 1 minus 5 times that is going to be what? Right? R2, I'm sorry, 1. R2 minus 5 times this is 0, and this is again it's going to be 0 here. And this one is what? This minus 5 times R1, 2 times, right? Sorry, 2 times. It's going to be minus 2 here, right? And this is going to be 0, and this is going to be 1. Am I right? Is it fine? So you can cross check that if I apply this same operation here, you will get this result, right? So this is really necessary to understand how the null space is, obtained from the matrix A, how the column space are obtained from that matrix A, right? All those things, right? So what I am trying to say here is, I have applied and you got this row reduced echelon form, but still this I wanted to make it a 0, right? So what I do is, again I do the same operation with this row, right? Will it be possible to? Yeah, but this itself is the row reduced echelon form, right? Actually, if I have a matrix of this form, right? So it is like this, one element followed by 2 zeros, or I put it as ABC, DE0, F00, and other things, is arbitrary, that we are not worrying about. We need to look for 3 columns in which all the one of the column we have all the 3 elements are non-zero, and we have a column with 2 non-zero and followed by 1 0, and another column with 1 non-zero followed by what? 2 zeros, right? That is the minimal requirement, right? Whatever the size you have it, this is what we call it as row reduced echelon form format. And you may have more than, other columns which has the same format, that doesn't matter, but minimal requirement is this. So once you do that, then you have to look for the pivot columns. So this is what we call it as this pivot, right? So here, this is what of this form I can choose, right? And we have other columns also. We have to choose the columns like this with all the elements as what? Non-zero, and 2 non-zero followed by 1 0, and 1 non-zero followed by 2 0. It may be in different places. For here, I call this is a pivot column, and this is the pivot column, and this is the pivot column here. This I will not choose. But here we have a choice. You can either choose this or this. It's up to you, right? But here we need to choose these two. Here, this two, among these two, we can have a choice. Either you can choose this as a pivot column, and this is a pivot column. So here, one of the column we have 3 elements which is non-zero, and here 2 elements non-zero followed by 1 0, and here 1 non-zero followed by what? 2 0. And this identifying these pivot columns is necessary to find out what all the columns in the matrix A are independent. Right? So here what I am trying to say here is I choose this vector, and this vector. These 3 vectors forms the independent vectors. It means that I can represent this vector, which is what? 4, 8, 3, as a linear combination of these 3 vectors. It is possible. If you solve, you will get a solution. I repeat, alpha 1 times this vector plus alpha 2 times this vector plus alpha 3 times this vector will end up with this vector for some values of alpha 1, alpha 2, alpha 3. That is the meaning of it. You understood what I am trying to say? Right? If one of the column, if the vector is represented as a linear combination of what? The other vectors, right? Then that is not going to be the independent one. That depends on these 3 vectors. But if I try to represent this vector using this vector, it is not possible. Alpha 1 times this vector plus alpha 2 times this vector equal to this. If I solve for alpha or alpha 2, you will not get a solution. You understood the point? But it is not true in all the cases. Right? If I have some arbitrary vector, it may also choose, for example, 1, 2, 4, right? And then 3, okay, I'll take it as a very simple 1, 1, 1. If I do some linear combination, right, let us see, simple addition itself is a linear combination. You may have a situation like this. In this case, just a linear combination of these 2 ends up with this. In that case, I cannot say that these 3 are what? Independent. You understood? You understood the point? Here what I am doing? 1 times this plus 1 times this is getting this, right? 1 plus 1 is 2, 2 plus 1 is 3, 4 plus 1 is 5. These 2 are what? These 2 are independent. But this vector depends on these 2, right? Vectors, right? You understood the point, right? So, more formally, the definition is like this. If I want to claim the vectors if I want to claim the vectors v1, v2, v3, they are independent. Some arbitrary vectors I am having, if you want to confirm whether these vectors are independent or not, the condition is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. If I equate to 0, if I equate this to 0, the only solution for alpha 1, alpha 2, alpha 3 is 0 itself. I must not able to find out, right? Right? The only choice for me to make this linear combination to end up with 0 is simply alpha 1 is equal to alpha 2 equal to alpha 3, that is equal to what? 0. If this condition satisfies, then we say that these v1, v2, v3 are what? Independent. Just like that, these 3 are independent. These three are independent, that is very obvious. Why? I cannot write this vector just by doing linear combination of these two, because some constant of 0, when you add it should end up with what? 0. It is not coming. Straight away it is not possible. We are able to understand these three are what? Independent. They are what we call it as pivot columns. We are actually looking for those columns. Not all the problems, right, end up with this structure. Sometimes, I'm just saying that, right, so I'll write at the bottom, I don't want to remove this, right, I use a different color. Sometimes, you may have 0 and 0 here, in place of -4 or -5. In that case, if I have a situation like this, then how many pivot columns you have? Only 2. You understood the point? Instead of -4 and -5, if it happens for some problem, if it happens to be 0 and 0, you are not having actually 3 pivot columns, you are having only what? 2 pivot columns. So they are all the independent one, right? So these pivot columns are independent one. So the corresponding columns of the matrix A, I am looking back again, this one, right? The corresponding columns of the matrix A, they are also independent. Actually, we are looking for the basis, right? First of all, you must know the difference between the spanning set and the basis. The spanning set. Spanning set means what? I already told you have a column space of the matrix A. So that is spanned. Means I do linear combination of some vectors which spans that space, right? So these 4 vectors are what we call it as spanning set. These 4 vectors I do what? The linear combinations that end up with what? The space is what we call it as spanning set. Now what I am telling is very important. The minimal spanning set is what we call it as basis. Minimal spanning set means you get, by doing this linear combination of these 4 vectors, we get a space, is called as column space of A. But to get that space, it is not necessary to have 4 vectors. It is enough for me to have either 3 vectors or 2 vectors or even what? 1 vector. Who knows? Right? Suppose if I have a matrix of this form. Suppose I have a matrix like this. I say that the spanning set is what? 1 0 0, 2 0 0, 3 0 0, linear combinations, and I end up with a space. But I can even claim that the same space can be obtained just by doing what? The scalar values of just one vector itself, 1 0 0, because 2 0 0 can be obtained just by multiplying what? 2 times the first vector, and 3 0 0 can be obtained just by doing what? 3 times the first vector, and the second vector and third vector itself is coming from where? The first vector. So why should I have second and third to span it? Understood? This case, the spanning set is 1 0 0, 2 0 0, 3 0 0, but the basis is just 1 0 0. That is what I am telling. So the minimal spanning set is what we call it as basis. Actually, we are looking for the basis. That's what the main problem what I am doing. Right? These columns forms a space. We got that column space of A, fine. But what is a minimal spanning set? The minimal spanning set, for the minimal spanning set, we have to choose the vectors that are what? Independent to each other. And these vectors are independent. These 3 vectors are independent. Right? And hence, you should not go for this. This is only for identifying which are all the columns or what? Independent. You should not go for this matrix. You have to come back to this matrix and you have to see the corresponding columns in this matrix, and we can claim that these vectors actually forms the basis for the column space of A. Right? So I say that for this case, I will write it here. I am looking for the basis. That's what I am doing. So the column space of A, the basis vectors are this. And you have a choice, in fact. I can choose either this column or this column as a pivot, right? So it is up to you, but I have chosen the first three. So it is 1, 5, 2, 2, 6, 4, and then 3, 7, 2. That forms a column space of A. Right? So now, what is that null space of A? Null space of A is what? Ax equal to 0, set of all vectors satisfying that condition, right? So it is like this, I have a matrix A, I am looking for X that satisfies this condition. If I multiply some other matrix here, B, that is also going to end up with what? 0. You understood the point? Right? So what I am trying to say here is, the null space of A is same as that of the null space of what? BA. Why I am bringing this point here, right, is because I did some multiplication, right, before. This is matrix A and this is like matrix B, right? This is A and this is like B. I multiply, I get this answer, which is row reduced echelon form. The null space of this is same as that of null space of this matrix A. That's what I want to tell. But column space are not same. Column space of matrix A and column space of this row reduced echelon form, they are not same. But we are able to identify the independent vectors. That is different. We are using this RREC, row reduced echelon form, to find out the independent vectors. But, right, the space, the column space of this and this are not same. But null space of this and this are same, because I wanted to use this one for finding out the null space of A, right? So I take this matrix for finding out null space, 1, 0, 0, 2, minus 4, 0, 3, minus 8, minus 4, and this is minus 5 here. I need to have some vector x to make it a 0 with this. And this vector x is of size 4 cross 1. And I have chosen a matrix which is not a good matrix for explanation, because the number of independent vectors here, it is 3. That is a natural thing, R3. For example, this case is M is what? 3 here. So this is basically R3. When I have a space R3, when I have a space R3, vector space, right, to span the complete space, right, means what? All the vectors with element, number of elements were 3. All the vectors with the number of elements 3. What is the basis for it? We have a standard basis which is just what? Yes, somebody is telling 1, 0, 0, 0, 1, 0, and what? 0, 0, 1. That's it. Any vector I can get with the 3 elements can be represented just by using these 3 bases. These vectors. This is what we call as basis vector. Right? The minimal spanning set, the number of vectors are going to be 3, and this is what we call as the rank of the matrix, or in vector space this is what we call as a dimension. Dimension of column space of A. Dimension of column space of A, in this case it is, I am talking about this R3. The dimension of R3 is what? 3. Number of vectors which spans the space is only 3. Why I am telling this one is, this is not good, because I got a column space of A only what? 3 vectors, right? It is same as that of what I am talking about, the 3 which spans the complete R3. Even though I am claiming that this column space of A is spanning what? The columns of the matrix A, which is also true that it spans what? The complete R3. You understood what I am trying to say? It spans the complete R3. What it really mean by that? You see that R3, I said column space of A is a subspace and null space of A transpose is going to be what? The subspace of it. Right? And I said now this column space of A is the complete R3. Then what does it mean? There is nothing like null space of A transpose. Only 0 vector is getting shared. It means that the null space of A transpose is going to be the 0 vector itself. For this example, if I have 2 pivot columns, then it is going to be a good story. That we'll get 2 vectors here and 1 vector here. But this case, as the number of vectors which spans the column space of A, which is same as that of what? The space which spans the complete R3, right? Your null space of A transpose is actually becoming 0 vector. Right? Right? That is one point. So now coming back to alpha 4. So it means that I can write alpha 1, alpha 2, alpha 3 all are in terms of what? Alpha 4. And that last one I keep as it is. This I am not disturbing. Right? And all other things I want to write in terms of what? Alpha 4. That is the way I am going to do now. So now for alpha 3 it is what? 5 alpha 4. That is what I am writing here actually. Minus 5 by 4, right? Isn't it? Am I right or wrong? 5 alpha 4, right? Alpha 3 is what? Minus 5 by 4 alpha 4. Am I right? Okay. Coming to this alpha 2. Alpha 2 is what? 8 alpha 3 plus what? 12 alpha 4 divided by what? Minus 4, right? But still, you know, I can represent this alpha 3 as what? Minus 5 by 4 alpha 4, right? So can you tell me what is that value? If I substitute alpha 3 as minus 5 by 4 alpha 4, somebody tell me I will write what you are telling. So I want the answer in terms of alpha 4, alpha 2. You tell? Minus alpha 4 by 2. And then alpha 1 in the same fashion. 3 alpha 4 by 4. Right? Isn't it? So this is my vector, right? I can choose this alpha 4 to be what? Any value which satisfies this condition that this times this is equal to what? 0. You can check if it is not coming, it is wrong. I mean, the computation is not correct. Right? You can choose this alpha 4 as 1, for example. Let us cross check. Alpha 4 as 1. So you get 3 by 4. This is minus 1 by 2. This is minus 5 by 4 and this is 1 here. If I do this multiplication, you are supposed to get 0. Are you getting or not? You just check. Are you getting this? So I can say that the null space of A is actually 3 by 4 minus 1 by 2 minus 5 by 4 and this is 1 here times what? Alpha 4. For alpha 4 what? Element of R. Right? So the null space of A is a space, right, spanned by a single vector like this by choosing any values of what? Alpha 4. Anybody check that? Are you getting 0? Huh? You checked, right? Good, thank you. Because I want to have confirmation. Right? So for any values of alpha 4, right, you get this matrix multiplied with this vector is going to be what? 0. And this is going to be your null space of what? A. Remember that. Because when I multiply this vector with that original A also, you will get 0. You can cross check that. Ax also will become 0. This is A here. A into this vector will also become 0. You can check that also. Right? So now null space of A is what? How many vectors you have for null space of A? It is only one vector. So here this is spanned by 3 vectors. Null space of A is actually spanned by what? One vector. Got it? And this 3 plus 1 is actually the number of columns of the matrix A. This will always be there. This is a cross check for me. Right? This is what we call it as rank nullity theorem. The column space of, or the dimension of, right? I'll write like this. So the dimension of the column space of A plus the dimension of the null space of A is equal to the number of columns of the matrix A. Here in this case the number of columns are what? 4. This is equal to 4. This case, this dimension of column space of A is 3. The dimension of null space of A is 1, and 3 plus 1 is 4 here. I don't want to do the other things, column space of A transpose and null space of A transpose. I want you to do today. Tomorrow I want to see the result alone. Just to take the transpose of this matrix A, do the same job. Getting column space of A transpose is nothing but you take the transpose and do the same job, right? So just take the transpose of A and do the row reduced echelon form. Find out the pivot columns. That forms what? The corresponding columns of the matrix A forms what? The column space of A transpose. Then whatever you had, this row reduced echelon form, from that you compute null space of what? A transpose, and in that case the dimension of this, I don't know what value you are going to get. Let us say that value is R1 here, and here this is going to be R2, and your R1 plus R2 should end up with what? 3. You just cross check. R1 plus R2 should end up with what? 3. That is one. And more important, I want to discuss tomorrow that one. Whatever the vector you get here, the basis vector, you have one more confirmation that we already got the basis for what? Column space of A, and I already told these two are what? Orthogonal. So if I take a dot product of this basis, that should end up with what? 0. Are you getting that? Also you can check. Tomorrow anyhow we are going to do that job, right? You understood? So you get a basis for this. You need to get a basis for this. If I do the dot product of these two, you are supposed to get 0. Dot product of these two will get 0. And now itself I know the answer for null space of A transpose, which we already did. What is it? We know the answer now. Null space of A transpose, we know the answer. Without doing all those things, I can tell the answer. It is 0. That I will tell now itself, because we know that column space of A is a subspace of R3, but it is not really subspace because the dimension of this one is 3, which spans the complete R3. So there is no vector in null space of A transpose except the 0 vector. Right? So now itself I am telling you do the formal thing. You do the formal method. You will get this as 0, but this will not be 0. You get some vectors here. Column space of A transpose. Right? So we will continue tomorrow from this point onwards. Just do column space of A transpose and null space of A transpose. Right? We'll stop here. Okay. We taken the attendance, no?